This is the pre-lab for the experiment on thin layer chromatography. In organic chemistry, sometimes the most time-consuming step in any synthesis is not performing the reaction itself, but rather purifying the desired material from any unwanted byproducts. There are a variety of methods used to purify organic reactions, and one technique that is commonplace is chromatography. The word chromatography got its name from its original use in separating mixtures of colored substances, but it is now used to separate many different types of organic compounds, colored or not. The experiment you will be running in lab will be on a specific type of chromatography called thin layer chromatography, or TLC. TLC is a separation technique that organic chemists use to visualize the identity, efficiency, and purity of chemical reactions. It is an indispensable technique in any organic chemistry lab, and one that we will revisit throughout the year. The pre-lab assignment for this experiment consists of reading the assigned sections in Techniques in Organic Chemistry, watching the videos on TLC setup and visualization from Morig, and preparing your laboratory notebook in an investigative format. When writing your procedure, be sure to leave enough room so that you can sketch each of your TLC chromatograms into your notebook in an organized manner. So let's discuss the theory of chromatography. Thin layer chromatography, or TLC, is a simple, inexpensive, and efficient analytical separation technique that requires less than 10 micrograms of material to perform. It is used in a wide array of laboratory applications. Commonly referred to as TLC, it can establish whether two compounds are unique, it can determine the number of components in a mixture, and it is used to analyze the purity of a reagent or product. It is also used to determine the effectiveness of other purification techniques, for example, extraction and recrystallization, or even a distillation if the liquid is non-volatile. Finally, it can be used to monitor reaction progress and identify when a reaction has run to completion. The components needed for running thin layer chromatography are quite simple. Some kind of TLC plate is required, shown here is a silica gel TLC plate. A developing chamber, either with a lid or wrapped in foil or plastic wrap, is needed. A small piece of filter paper will be used to wick the solvent throughout the chamber, keeping the vapor pressure even throughout. A pencil is needed to mark the TLC plate, and a capillary tube or micropipette is used to apply the sample compound. Finally, an elution solvent or mobile phase will be placed inside the developing chamber. As I mentioned, TLC is a separation technique, but more specifically, it is a liquid-solid partition, where an equilibrium exists between a liquid and solid phase. The stationary or solid phase is a thin layer of adsorbent that coats a glass, metal, or plastic plate. This is normally silica gel or alumina. The mobile or liquid phase is a solvent or solvent mixture that rises up the plate by capillary action. Examples of this would be a solvent like dichloromethane, or a mixture like 4:1 hexanes acetone. The key to a successful separation hinges on the following. A small amount of sample is placed on the TLC plate, and the plate is then eluted with a solvent. An equilibrium is established between the two phases, the mobile phase and the stationary phase. Compounds will adsorb or stick onto the stationary phase via intermolecular forces. Strong interactions with the stationary phase will cause the compounds to stick tightly. Compounds are then desorbed or released with a suitable mobile phase, and they travel up the plate. The rate of this travel is dependent on the equilibrium that exists between both phases. So let's try to think of this using an everyday analogy. Say you and your friend decide to head to the mountains over winter break for some skiing and snowboarding. You both start at the top of the mountain at the same time and on the same trail. As you begin your descent, you begin to pull away from your friend, who travels farther behind. You reach the bottom first, while your friend reaches the bottom more slowly. So how can we explain this? while you, the skier, like to make sharp, quick turns, so you spend less time interacting with the snow, thus reaching the bottom faster. Your friend, however, likes to make large looping turns, so he or she spends more time on the mountain and reaches the bottom second. This analogy can be used to understand TLC. Let's say we have a silica gel TLC plate. Silica gel is silicon dioxide that is bound together to a solid surface that bears free hydroxyl groups on one face. We can think of a plate, then, as having OH groups sticking up. Since OH groups are capable of hydrogen bonding and other dipole-dipole interactions, we say that the surface of the stationary phase is polar. If we have a mixture of three compounds, say naphthalene, benzoic acid, and benzyl alcohol, we can attempt to separate these three on the silica gel plate due to differences in their polarity. Naphthalene is a nonpolar molecule, consisting of only carbon-carbon and carbon-hydrogen bonds that make the molecule very hydrophobic. Benzoic acid and benzyl alcohol, on the other hand, contain functional groups that are polar. The carboxylic acid functional group of benzoic acid has a highly acidic proton with a pKa of 4. And benzyl alcohol contains an alcohol functional group that is capable of hydrogen bonding and other dipole-dipole interactions. In these two molecules, the other half is very nonpolar, consisting of benzene rings with only carbon-carbon and carbon-hydrogen bonds. If we were to compare the dipole moments of these three molecules, we would see that naphthalene does not have a dipole moment, but benzoic acid and benzyl alcohol have large dipole moments. If we were to spot these three compounds, which I will label A, B, and C, on a silica gel plate as shown, and elute them with a solvent such as dichloromethane, I may obtain a separation that looks like this. Since naphthalene is nonpolar, it makes very little interaction with the stationary phase, which consists of polar OH groups. So when a mobile phase comes along, it preferentially dissolves in the mobile phase instead of remaining stuck onto the TLC plate. In other words, the intermolecular forces between naphthalene and dichloromethane are stronger than between naphthalene and silica gel. Benzoic acid, compound B, on the other hand, is very polar with a dipole moment of 1.72. It has very strong hydrogen bonding and dipole-dipole interactions with the silica gel, so it sticks very, very tightly. When dichloromethane is used to develop the plate, benzoic acid prefers to stick to the silica gel rather than dissolve in dichloromethane, since the intermolecular forces between benzoic acid and silica gel are stronger. Then we have benzyl alcohol, which is slightly less polar than benzoic acid, with a dipole moment of 1.67. If benzyl alcohol is less polar, we should expect that it will stick less tightly to silica gel and move up the TLC plate higher than benzoic acid, but not nearly as high as naphthalene. Now this would be characterized as an ideal TLC separation. What would a TLC look like where the spots are not as separated as much? In other words, is there a way to move these spots higher or lower on a TLC plate in case your first choice of an elution solvent does not give you the best separation? We call this adjusting the polarity of the eluting solvent. If we take the same TLC plate that we prepared before, but this time elute with ethyl acetate, we will obtain a much different chromatogram. Ethyl acetate is much more polar than dichloromethane. We see that the net result now has all three spots shifted higher up the plate. All three compounds interact more with the mobile phase, which disrupts the intermolecular forces, causing the compounds to absorb to the silica gel. The equilibrium then shifts towards the mobile phase, and the compounds travel up the plate faster. Contrast this with a TLC where hexane is used as the eluent. Since hexane is nonpolar, we should expect that each compound will travel up the plate slowly. In this case, the interaction with the stationary phase is so strong that the mobile phase is not polar enough to disrupt these intermolecular forces. The equilibrium shifts towards the stationary phase, and the compounds travel up the plate more slowly. It is important to note that even though I have illustrated changing the mobile phase to adjust the polarity, the stationary phase may also change. A TLC plate can be also coated with something nonpolar. For example, a C18 coating is a nonpolar stationary phase that has a long 18-carbon chain on the surface. This will cause nonpolar compounds to stick more tightly, the exact opposite from what we saw with silica gel. So how do we actually set up a proper TLC plate? First, dissolve the sample in an appropriate solvent. This should be a volatile solvent, usually something like dichloromethane, acetone, or ethyl acetate. Make sure that the concentration of this sample is not too high, otherwise the spot will bleed throughout the TLC plate, but also not too dilute, since you may not be able to visualize it later. Often it is best to look at the TLC under a UV lamp once you make a spot to ensure that it has the correct concentration. Next, grab a TLC plate and draw a line in pencil approximately 1 centimeter from the bottom of the plate to mark the origin, also known as the baseline. Next, using a capillary tube, draw up and dispense a small amount of sample onto the plate and let it evaporate. Place your eluent in the TLC chamber and then stick a piece of filter paper onto the walls of the chamber to wick up the solvent. This will help to make sure that the vapor pressure is even throughout. Develop the TLC plate by placing it directly vertical into the chamber. Once the eluent reaches the top of the plate, remove the plate and make the eluent front with a pencil. Allow the plate to dry and then visualize the compounds. Visualization of the compounds is an important step because most organic compounds are not colored. The TLC plates that you remove from the chamber after the solvent reaches the top will look mostly like this, a blank plate. So where are the compounds? The reason that we don't see them is because they do not absorb light in the visible region of the electromagnetic spectrum. However, there are several other methods of visualization that do work. Most compounds, if they contain conjugation or aromaticity, will absorb light in the ultraviolet region. We use an ultraviolet lamp to observe this absorption. Iodine vapor can also be used to visualize compounds on a TLC plate. Finally, we often use staining methods to visualize organic compounds. For example, anisaldehyde will react with compounds on the plate that contain certain functional groups. What you may notice from these three visualization methods is that not all techniques will enable you to see all compounds. So it is often the case that we want to use multiple methods for visualization. So once we see our spots, we want to quantify our results. We do this by calculating what's known as the retention factor. The RF is simply a ratio between the distance traveled by the compound itself to the distance traveled by the eluent front. So for example, if we have a TLC that has been visualized with UV light to look like this, we can calculate the RF. The denominator will be the distance from the origin to the eluent front, while the numerator will be the distance from the origin to the center of the compound spot. In this case, we have a RF equal to 20 millimeters divided by 80 millimeters, which gives us a value of 0.25. It is important to note that RF values should be reproducible. The same compound eluted under identical conditions should give the same RF.